Right now, as you're watching this video, humanity's most incredible achievement is about to reach one light day away from Earth. Not toward another star, not toward some distant galaxy, just one light day, one single day of light travel distance. And that's Voyager 1, a spacecraft that's been flying non-stop for nearly 50 years. 50 years of continuous, uninterrupted flight through the vacuum of space at 38,000 miles per hour. That's faster than a speeding bullet. That's faster than anything humanity has ever created and pointed into the void. And after half a century at maximum velocity, it has only traveled one light day. Now, the nearest star to Earth is Proxima Centauri. It sits approximately 4¼ light years away. Do you know how long it would take Voyager 1, the fastest object we've ever built, to reach that star at its current velocity? 73,000 years. That's longer than the entire history of human civilization, longer than the span between the last ice age and today. Every empire that has ever risen and fallen on Earth, Sumer, Rome, the Mongolian, the British Empire, could fit inside that travel time with centuries to spare. But here's the thing that keeps me up at night. The real horror of interstellar travel isn't the distance. Distance is just a number. Large numbers are hard for our brains to comprehend, sure, but they're still just math. The real horror, the thing that breaks human beings, is what the distance does to every single system keeping you alive. Radiation shatters your DNA, cell by cell, and there's no hospital in the universe to save you. Life support fails, because all machines fail eventually, and there's no replacement parts arriving on the next supply ship. Communication with Earth becomes a one-way monologue into absolute silence. A real interstellar mission doesn't just test engineering. It tests something far darker. Whether human beings can remain human across a void that erases every safety net our species has ever known. If you enjoyed journeys that completely reshape how you see humanity's place in the cosmos, please do me a favor, hit that like button and subscribe. Now brace yourself. Let's begin. Part 1. The History of Safe Space Travel. Section 1A, Apollo 11 and Earth's Tether. On July 20th, 1969, something profound happened. Neil Armstrong's boot pressed into lunar soil, and for the first time in human history, we stood on another world. We touched another sphere. We proved that we weren't bound to Earth. And yet, and this is crucial, we were never truly beyond help. The Apollo 11 mission lasted 8 days, 3 hours and 18 minutes from launch to splashdown. During that entire journey, during the ascent, the journey to the moon, 21 hours on the lunar surface, the journey back Earth was never more than about 1.3 light seconds away. That means a radio signal from Mission Control in Houston traveled through space and reached the crew. They heard the message, and within about 3 seconds, they could respond. 3 seconds, that's the communication delay for the moon. 3 seconds feels like an eternity in a crisis, but it's still real time. It's still a conversation. Mission Control could guide the astronauts through procedures. They could solve problems together. The signal was thin, yes, but it was real. And if something catastrophic happened, if an oxygen valve failed mid-journey, or the navigation system went haywire, the astronauts could abort and return home within days. Days. Not weeks, not months, not years, days. The safety net was thin, fragile, almost terrifying by today's standards, but it existed. The ground was always listening. Help was always close. Every human being who has ever traveled into space has operated within that thin safety net. And this is where our story of survival takes a darker turn. Section 1B, the International Space Station, still connected. Today, the International Space Station orbits just 250 miles above Earth's surface. That's actually closer than the distance from New York to Washington, D.C. On a clear day, the astronauts aboard the ISS can look down through the cupola windows and see the entire planet. They can see the continents, the oceans, the clouds swirling over storms. Earth is right there, visible, tangible, real. And what about supplies? Resupply spacecraft dock at the station every few weeks, carrying food, fresh water, spare parts, equipment, and even mail from home. Mail, think about that. If an astronaut is going through a rough patch mentally, they can receive a handwritten letter from their family. That psychological lifeline matters in ways that are hard to quantify. But it goes further. The ISS has permanently docked evacuation capsules at all times. If a medical emergency strikes, a severe infection, appendicitis, cardiac issues, an astronaut can be in that capsule within hours and back on Earth, receiving world-class medical treatment within hours more. Not days, hours. The most sophisticated surgery can be performed. The best doctors on Earth can directly treat the condition. And if psychological problems emerge, depression, anxiety, extreme homesickness, the crew member can come home. They're not stuck. They're not trapped. The psychological reality of the ISS is profound. Earth is always right there, visible, reachable by radio in less than a second, with immediate rescue possible at any moment. No one aboard the ISS is truly alone. No one is truly beyond rescue. This will become extremely important as we venture further into the cosmos. Section 1C, The Limits of Safety. Why Apollo 13 survived. We can't talk about space exploration without addressing the disasters that nearly happened. Apollo 1 took 3 astronauts. Apollo 13 nearly took 3 more. On April 13, 1970, 200,000 miles from Earth, an oxygen tank exploded in the lunar module. It wasn't a small problem, it was catastrophic. The crew was in mortal danger with every passing second. The command module was losing power, oxygen was venting into space, CO2 was building up to toxic levels. By every logical assessment, those 3 men should have died. They should have become 3 frozen bodies drifting through space, a permanent reminder of humanity's ambition exceeding our capabilities. But Apollo 13 succeeded in bringing those astronauts home precisely because, and listen to this, because Earth was close enough to help. Engineers in Houston worked continuously, sleeping in shifts, improvising emergency solutions on the fly. They figured out how to repurpose a lunar module, designed as a spacecraft for 2 people on the surface, into a lifeboat for 3 people returning home. They guided the astronauts through impossibly complex procedures in real time. Every single problem was solved collaboratively between Earth and space. The journey home took 3 days. 3 days of constant problem solving, of innovation under impossible pressure, of machines and human minds working in perfect synchronization. 3 days, and everyone came home. The distance was manageable. The lifeline held. Earth could reach out and pull them back. And that ability to rescue, to guide, to collaborate, it will become the most precious thing humanity loses as we venture further into the cosmos. Part 2, the Mars Threshold. Now let's talk about Mars. No human has ever set foot there. No astronaut has even attempted the journey. But every space agency, every advanced nation, is planning to do exactly that in the coming decades. And Mars is where the safety net begins to fray. Mars sits approximately 34 million miles from Earth at its closest approach. That's the distance when the 2 planets are aligned on the same side of the Sun. But our solar system is dynamic. Planets move in elliptical orbits. Sometimes Mars is closer. Sometimes it's much farther. Light takes between 3 and 22 minutes to travel between Earth and Mars depending on orbital positions. Think about what that means for real-time communication. You send a message from Mars to Earth. It takes up to 22 minutes to arrive. Mission Control reads it, formulates a response, and sends it back. Another 22 minutes minimum for the return journey. A round-trip radio conversation can take up to 44 minutes. Nearly 3/4 of an hour for one exchange of information. Now imagine there's an emergency. A dust storm is destroying solar panels. A water recycler has failed. An astronaut is suffering from acute psychological distress. The crew sends the message. We have a critical problem. Earth receives it 22 minutes later. the best minds on the planet work frantically to solve it. But they can't send real-time guidance. They can't see what's happening. They can't adjust their instructions based on the astronauts' live responses. The Mars crew has to become autonomous. They have to become engineers, doctors, mechanics, and psychologists, all in one. Mission Control can provide guidance, but that guidance has a communication delay built into every interaction. Real-time problem solving becomes impossible. And the journey itself, the crewed trip from Earth to Mars in a spacecraft designed with current technology, would take roughly 7 to 9 months each way. 7 to 9 months in a confined spacecraft with limited room, limited supplies, limited space for exercise. The crew would spend that time watching Earth recede behind them, getting smaller day by day until it becomes just another star in the sky. No opportunity to turn back. No possibility of emergency return. Once they arrive and land on the Martian surface, the mission would likely last 2 to 3 years. 2 to 3 years exploring a barren desert world, conducting science, building habitat infrastructure, then another 7 to 9 month journey back. We're talking about a mission that could last 4 to 5 years total. 4 to 5 years, that's longer than most PhD programs. It's longer than most military deployments. It's long enough that the astronauts, children back on Earth will enter elementary school and advance significantly through their education. Long enough for technology to advance, for social situations to change, for the entire political landscape to shift. And the health effects? NASA has spent decades documenting what happens to the human body in space. Even 6 months aboard the International Space Station, a facility orbiting 250 miles above hospitals with the best doctors on the planet, causes significant physiological degradation. Section 2A, the physical toll of space. Bone density loss begins within the first few weeks of weightlessness. An astronaut can lose 1% of their bone mass per month in microgravity. That might not sound dramatic until you realize that we normally lose about 1% per year as we age. In space, aging is accelerated. After 6 months, the astronauts lose approximately 6% of their bone density. That's equivalent to 6 years of terrestrial aging. Muscle atrophy is even more pronounced. Without gravity pulling on the muscles, they have no reason to maintain their strength. The body is efficient. If a muscle isn't needed, it's broken down and the amino acids are recycled. An astronaut can lose up to 20% of their muscle mass after 6 months in space. That's like going from an athlete to someone who's been bedridden for months. Cardiovascular deconditioning is brutal. The heart is a muscle, and in weightlessness, it doesn't have to pump as hard. The cardiovascular system essentially goes on a vacation. After 6 months, astronauts experience significant loss of cardiovascular fitness. Their maximum oxygen uptake decreases. Upon returning to Earth, some astronauts can barely stand for extended periods. Vision impairment is less understood, but deeply concerning. Some astronauts develop what's called spaceflight-associated neuroocular syndrome, or SANS. Their eyesight actually degrades. The optic nerve swells. The shape of the eyeball changes slightly. For some people, this effect is permanent. They return to Earth with permanently degraded vision. Immune suppression is another horrifying effect. The human immune system evolved in a 1G gravitational environment. In zero gravity, the immune system becomes suppressed. Infections that would normally be fought off easily can proliferate. Astronauts are more susceptible to respiratory infections, fungal infections, and even tumor development. And radiation. We'll get deep into radiation in a moment, but for now, know that even inside low Earth orbit, astronauts are exposed to elevated levels of cosmic radiation. Outside the protective magnetosphere, those levels increase dramatically. Psychological strain is the final piece. Confinement in small spaces with the same people for months creates psychological stress that's hard to overstate. Some astronauts experience depression. Others experience existential crises. Watching your home planet recede to a tiny blue dot while you're trapped in a metal tube creates a psychological pressure that no amount of training can fully prepare you for. And here's the critical point. all of these problems get significantly worse as mission duration increases. 6 months on the ISS is hard. 2 to 3 years in deep space with no possibility of quick return would be brutally hard. 3 years of continuous muscle loss, bone degradation, radiation exposure, and psychological confinement would produce astronauts who are barely recognizable as the healthy humans who departed Earth. Section 2B, the mental trap of comparison. But here's where human intuition plays a dangerous trick on us. When people hear about a Mars mission lasting 3 to 5 years, they unconsciously perform a simple mental calculation. They think, Mars is a longer trip, so it requires more supplies. Yes, absolutely. But it's still the same kind of challenge. Harder, certainly. More supplies needed, absolutely. But fundamentally the same, just stretched out over more time and more distance. That assumption is catastrophically wrong. A Mars mission is harder than Apollo or the ISS, yes, but it's still within the realm of human capability. Barely. The journey is long, the isolation is profound, but help is still theoretically possible. It's still a mission with a clear endpoint. It's still an expedition. But now let's take that Mars mission and imagine it lasting not 3 to 5 years, but 40 years, or 100 years, or 500 years. That's when we cross into a category of human experience that has no precedent in our entire history. That's the difference between a mission and a civilization. That's the difference between leaving home and becoming homeless. Part 3. The Interstellar Problem, Scales that Break Comprehension. The nearest star system to our Sun is called Alpha Centauri. It's a triple star system, 3 suns orbiting each other in a complex gravitational dance. At the outer edge of this system orbits a small red dwarf star called Proxima Centauri, and Proxima Centauri is our nearest stellar neighbor. The distance is 4.24 light-years. Now that's a number we've all heard before, 4.24 light-years. It sounds small because we've abstracted it into a simple number, but let me make this visceral for you. 1 light-year is the distance that light travels in 1 year, moving at 186,000 miles per second. That's not kilometers, that's miles per second. Light is literally the fastest thing that exists in the universe. And in 1 year of traveling at that incomprehensible speed, light covers a distance called 1 light-year. 1 light-year equals approximately 5.88 trillion miles. That's a 5 followed by 12 zeros. Trillion. It's a number so large that our brains literally can't process it. We can say it, we can write it down, but we can't truly comprehend what it means. Now multiply that by 4.24, and the distance to Proxima Centauri comes to approximately 25 trillion miles. Written out in full, that's a number with 13 digits before the decimal point. But numbers on a page mean nothing, they're abstractions. Let me compare this distance to something we've actually done in space. Section 3A, Voyager 1 and the Scale Problem. Voyager 1 was launched in 1977. That's nearly 50 years ago. Since then, it has been flying through space continuously, non-stop, without interruption or refueling. It's a robotic spacecraft, a machine that operates on solar panels and nuclear batteries. Voyager 1 is the fastest and most distant human-made object ever to fly through space. It's traveling at roughly 38,000 miles per hour relative to the Sun. That's 10.5 miles per second, faster than anything Apollo ever flew. Faster than the International Space Station. Faster than any spacecraft humanity has ever built. In November of 2026, which is right now as you're listening to this, Voyager 1 is about to reach a distance of 1 light day from Earth. 1 light day. That means a radio signal from our planet will take 24 full hours to reach the spacecraft. Think about that. After 5 decades of uninterrupted flight at 38,000 miles per hour, the fastest object humanity has ever built, Voyager 1 has only gone 1 light day. 1 day of light travel distance. Proxima Centauri is not 1 light day away, it is 4.24 light years away. That is approximately 550 light days. Voyager 1 has covered less than 1/1500th of the distance to the nearest star. If Voyager 1 were aimed directly at Proxima Centauri, it would arrive in roughly 73,000 years. That is not a typo. 70,000 years. To give this context, modern humans began migrating out of Africa about 70,000 to 100,000 years ago. The last ice age ended about 12,000 years ago. The invention of writing happened about 5,000 years ago. Jesus Christ was born about 2,000 years ago. Every empire that has ever risen and fallen on Earth, Sumer, Egypt, Babylon, Rome, the Ottomans, the British Empire, all of them, could fit inside a 73,000-year time span with multiple millennia to spare. And Voyager 1, the fastest spacecraft we've ever created, would still take that long to reach the nearest star. Section 3b, can we go faster? The propulsion problem. Obviously, no one proposes sending a crewed spacecraft at Voyager speeds toward another star. The entire point of interstellar propulsion research is to go dramatically faster. So the question becomes, what happens when we assume much better engines? What does the timeline look like with advanced propulsion? The answer depends on which propulsion concept you consider. There are several theoretical options, but every single one of them, every realistic option that doesn't violate known physics, delivers the same uncomfortable conclusion. The trip is still extraordinarily long. Let's start with nuclear thermal propulsion. This is the most mature advanced propulsion concept currently under active development by NASA and the Department of Defense. A nuclear thermal engine works by using a nuclear reactor to heat hydrogen propellant and then expelling it at high speed from the spacecraft. The theoretical performance is impressive compared to conventional chemical rockets. A nuclear thermal engine can roughly double the efficiency of a chemical rocket. Double. That sounds significant. And for missions within our solar system, getting to Mars faster, or exploring the outer planets, it's genuinely valuable technology. But here's the problem. Even doubling the efficiency of a chemical rocket still leaves you traveling at a tiny fraction of light speed. A nuclear thermal spacecraft might achieve speeds on the order of tens of thousands of miles per hour, maybe 30,000 or 40,000 mph, which is faster than Voyager 1, but not dramatically faster. At those speeds, the journey to Proxima Centauri would still require tens of thousands of years. Not 73,000 years anymore, maybe 30,000 or 40,000 years, but still tens of thousands. The technology is real and valuable for missions within our solar system, but it doesn't even begin to solve the interstellar problem. So let's consider something more ambitious: nuclear pulse propulsion. This concept was studied seriously during Project Orion in the 1950s and 60s. The idea is genuinely wild. You load the spacecraft with nuclear explosives. You place a massive pusher plate, a thick disc made of refractory materials, behind the spacecraft. Then, you detonate a nuclear bomb behind that plate. The explosion pushes the plate forward. The plate is connected to the spacecraft by shock absorbers, so the spacecraft accelerates forward without being instantly vaporized. You repeat this process hundreds or thousands of times. Each nuclear explosion pushes the spacecraft faster and faster. It sounds insane because it is insane. But the theoretical physics works, and the theoretical performance is impressive. A well-designed nuclear pulse vehicle might achieve speeds in the range of 3 to 5% of light speed. 5% of light speed, that's 600 miles per second. That's nearly 20 million miles per hour. At that velocity, the journey to Proxima Centauri would take roughly 85 years. 85 years. That's within the span of a single extended human lifetime, barely. Someone could depart at age 20 and arrive at age 105. It's possible. It would require someone to live longer than most humans currently do, but it's physically possible within human lifespan. But here's the catch: nuclear pulse propulsion has never been tested. Not even once. The engineering challenges are immense. Building a spacecraft strong enough to withstand hundreds of nuclear explosions firing next to it is an engineering problem we haven't solved. And internationally, treaties currently prohibit nuclear detonations in space. It's not a technological problem anymore. It's a political and legal barrier. So nuclear pulse propulsion remains a concept rather than a technology. It's theoretically possible, but possible and practical are different things. Now let's move into even more speculative territory, fusion propulsion. If humanity could build a working fusion rocket, a spacecraft that sustained controlled nuclear fusion reactions and directed the energy as thrust, we might achieve speeds on the order of 5 to 10% of light speed. 10% of light speed. At that velocity, the trip to Proxima Centauri would shrink to roughly 43 years. A crew that departed Earth in their 20s might arrive in their 60s. That starts to sound almost manageable. Retirement on an alien planet. You could spend your entire career on the voyage, and by the time you arrive, you're ready for retirement anyway. Except, and this is the crucial exception, this calculation assumes constant acceleration and constant deceleration. It assumes you can push the engines at maximum thrust for the entire 22-year journey. But these spacecraft still need fuel, and fuel has mass. And the more fuel you carry to decelerate at the destination, the more mass you have to accelerate at the beginning. This becomes a physics problem called the rocket equation, and it's brutally unfair. It means that realistic mission profiles, accounting for the fuel needed for both acceleration and deceleration, tend to push travel times back up toward a century or beyond. And more importantly, no fusion rocket capable of sustained thrust has ever been built. Not even at the proof of concept level. We have fusion experiments that produce more heat, yes, but sustained, controlled fusion that can be directed as rocket thrust? That remains science fiction. The most optimistic near-term interstellar propulsion concepts don't use rockets at all. They use light itself. There's a concept called laser-propelled light sails. An enormous ground-based laser array shoots a beam of light at a spacecraft with a massive gossamer-thin sail. The light pushes this sail. This sail accelerates. No fuel needed, no rockets, just photons carrying momentum. A project called Breakthrough Starshot, funded by billionaire Yuri Milner, proposed using this concept to accelerate gram-scale probes to 20% of light speed. Gram scale. That's a probe smaller than your hand. Not a crewed spacecraft, not a colony ship, a tiny robot carrying instruments. At 20% light speed, a probe could reach Proxima Centauri in roughly 20 years. 20 years. That's fast enough that a single spacecraft could make the journey and send back data about the star system. For scientific exploration, that's genuinely revolutionary, but it requires wafer-thin robotic sensors, not a crewed spacecraft big enough to keep humans alive. Scaling laser sail propulsion to push a vessel large enough to sustain human life would require energy inputs and sail dimensions that don't exist in any engineering roadmap. We're talking about a sail square miles in area. We're talking about power requirements measured in gigawatts. The physics might work, but the engineering doesn't exist yet and might never exist. Light sails may one day deliver our first close-up images of another star system, but they will not carry people. Section 3C, the propulsion conclusion. When you survey the full landscape of plausible propulsion technologies, everything from nuclear thermal rockets to laser sails, a sobering pattern emerges. Under the most optimistic, realistic assumptions, a crewed interstellar mission to the nearest star would take somewhere between 40 and several hundred years. Under more conservative but still ambitious assumptions, the journey extends to many centuries, or even millennia. Under anything resembling current technology, the timescale is tens of thousands of years. There is no magic shortcut hiding in known physics. Faster than light travel? That violates the fundamental structure of space-time. Wormholes? Interesting mathematically, but they require exotic matter with negative mass energy density, something we've never observed and might not exist. Warp drives? Same problem, same speculation, no experimental support whatsoever. The speed of light is not a suggestion. It's not a barrier we can negotiate with. It's a wall, a physical law of the universe as fundamental as time itself. And that wall sets a hard minimum on how long an interstellar journey must take. Part 4. The categorical shift from expedition to civilization. And here is where the fundamental nature of the interstellar problem changes. This is the moment where we shift from asking, "Can we get there?" to asking, "Can we survive it?" This is where space exploration becomes something entirely different. A space mission lasting days or weeks is an expedition. Astronauts are selected, trained, and deployed on a specific mission with a defined objective and timeline. They know they're coming home. They know their families will see them again within a specific window. The Apollo missions fit this category. The space shuttle missions fit this category. The long-duration ISS rotations fit this category. A space mission lasting months is a different beast. It's no longer a quick expedition. It's an endurance test. The crew deals with psychological strain, physiological degradation, and the cognitive load of complex operations in a confined environment. But it's still bounded. There's still an end date. There's still the knowledge that home is waiting. The journey to Mars, if it ever happens, would fit this category. It's hard. But it's still a trip with a departure and an arrival, bookending a defined period of hardship. But a mission lasting decades to centuries occupies an entirely different category of human experience. It's no longer a trip. It's no longer even an endurance test. It becomes a way of life. For a multi-century mission, it becomes the only way of life that most people aboard will ever know. Think about what that means. The original crew who launches the mission will age. They'll work during their prime years. And then they'll retire. And eventually, they'll die. They will spend their entire lives aboard a spacecraft hurtling through the void, knowing they'll never see their destination. They've sacrificed their entire existence for a goal they'll never personally achieve. Their children will be born aboard the ship. They'll grow up in artificial lights, in recycled air, in a metal environment with artificial gravity. The only world they'll ever know is the inside of a spacecraft. They'll work, raise families, and die aboard the ship, still decades or centuries away from the destination. The grandchildren of the original crew might also die aboard the ship, and the great-grandchildren, and the great-great-grandchildren. Depending on the travel time, the people who finally arrive at the destination star could be separated from the original crew by dozens of generations. Dozens of generations. That's like finding someone alive in 2026 who is a direct descendant of someone from the year 1026. 1,000 years of genealogical connection, all contained within a single spacecraft. This is not a longer version of going to Mars. This is fundamentally, categorically different. This is no longer human space exploration. This is human space colonization. And the colony is in motion, hurtling through the void. Section 4A, the problem of maintenance and knowledge. Now here's something that doesn't get talked about enough. Maintaining complex systems requires knowledge. It requires specialists. It requires institutions. The International Space Station operates with constant resupply from Earth, constant communication with thousands of engineers, and the ability to send specialists when critical repairs are needed. But even with all those advantages, maintaining the ISS is incredibly difficult. The station requires constant work, constant upgrades, constant problem solving. Now imagine a spacecraft much larger than the ISS, carrying hundreds of people, traveling for centuries with no resupply, no communication beyond a one-way monologue, and no possibility of sending specialist engineers when something fails. Every system that breaks, the crew has to fix. Every problem they have to solve. They have to maintain complete knowledge of every single system aboard the spacecraft. This is where generational knowledge becomes a critical problem. The original crew knows how to operate and repair every system. They spent their lives learning this stuff. But knowledge doesn't transfer easily. Even with documentation, with training manuals, with every effort to preserve institutional knowledge, there's a natural erosion of understanding across generations. Think about it. Your great-grandfather was an expert mechanic. He understood every system of his car perfectly. But did his knowledge transfer to you? Probably not. You might know that cars have engines and need oil, but you probably can't diagnose or repair complex problems like he could. Institutional knowledge, once lost, is extraordinarily difficult to recover. On an interstellar spacecraft, the generational transfer of knowledge is literally a matter of life and death. If the knowledge of how to operate the life support system is lost, people die. If the knowledge of how to repair the water recyclers is lost, people die. If the knowledge of how to maintain the radiation shielding is forgotten, people die. There's a phenomenon called technological regression. Small, isolated communities have historically shown patterns of losing technical knowledge over generations. The Romans built aqueducts and roads and structures that stood for millennia, but over the centuries, the knowledge of how to build such things was lost. It took until the Renaissance, over 1,000 years, to recover that lost knowledge. Now apply that concern to a sealed spacecraft where there's no connection to Earth, no library of billions of books on the internet, no backup civilization that retained the knowledge. If the crew forgets how to operate a critical system, they can't just call someone back on Earth. They can't just look it up online. They have to figure it out from first principles, or they die. This is the knowledge problem, and it's fundamentally unsolvable with current technology. You can create the best documentation possible. You can mandate that every generation learns specific skills. But you're fighting against human nature itself. People are busy. They have jobs. They have children to raise. They have relationships to maintain. And if they're not directly engaged with operating a particular system, then knowledge atrophies. Section 4b, the psychological abyss. And then there's the psychological problem, which might be even worse. What does it do to the human mind to grow up your entire life knowing you'll never see the destination? To know that your children will also die aboard the ship without ever reaching the destination? To know that your purpose, the entire reason humanity launched this mission, is something you'll never personally achieve? The original crew has motivation. They chose to go. They made a sacrifice knowing it would contribute to a grand goal. But what about the second generation? What about the fifth generation? What about the 10th generation? There's a concept in psychology called generational motivation loss. If an original goal is meaningful to the founder, but the cost of achieving it is spread across multiple generations, each generation feels less connection to the original goal. They experience the cost, confinement, lack of freedom, constant danger, without personally experiencing the reward. After 5 generations, the original mission goal might feel completely abstract. We're on this ship to reach Proxima Centauri 40 generations from now. It's almost meaningless. It's like asking someone to sacrifice their freedom today to benefit someone who won't be born for 1,000 years. Most people won't do that willingly. Most people will rebel. There's also the problem of what I'll call existential nihilism. Humans need purpose. We need meaning. We need to feel like our lives matter, like our work contributes to something important. But aboard an interstellar spacecraft, multiple generations will live entire lives knowing that they're just passing time until the next generation takes over. It's profound hopelessness. It's institutional despair. Some of the original crew members might handle this. They have the memory of Earth. They have the memory of blue skies and open oceans. But subsequent generations won't have that. The ship is all they've ever known. And confinement in a metal box for your entire life, with no hope of ever leaving, is a psychological prison that might drive people mad. We've seen evidence of this in historical examples. Prisoners held in solitary confinement often develop severe psychological problems. Sailors trapped on ships during long voyages have reported psychological deterioration. Astronauts, even on the short 6-month ISS rotations, report psychological strain. Now multiply that across centuries, across entire lifespans, with no possibility of leaving, no possibility of going home. The psychological toll could be devastating. It could lead to depression, to violence, to social breakdown. It could lead to crews that are so psychologically damaged that they can't maintain the spacecraft properly. And if the spacecraft isn't maintained, everyone dies. Part 5. The hostile environment. We've talked about the challenges of time, of knowledge, of psychology. But there's a fourth dimension to this problem, and it might be the worst of all. The environment outside the spacecraft isn't just empty, it's actively hostile. Within our solar system, there's actually some level of structure and protection. The sun's influence creates something called the heliosphere, a bubble of solar wind that extends beyond the orbit of Pluto and partially deflects the most energetic particles from deep space. Planets and moons provide gravitational landmarks for navigation. The sun provides light, heat, and a reference point. Space within the solar system is dangerous, yes, but it's not completely empty. It's still a neighborhood of sorts. There are resources. There are places to stop and resupply, at least theoretically. The sun is always there, like a lighthouse in the darkness. But beyond the heliosphere, all of that disappears. Beyond the heliopause, all of that protection vanishes. And an interstellar spacecraft would spend the vast majority of its journey outside the heliosphere, in the deep void between stars. Interstellar space is a near-perfect vacuum stretching for trillions of miles in every direction. To give you scale, the density of matter in the interstellar medium averages roughly 1 atom per cc, 1 atom. For reference, the air you're breathing right now contains approximately 25 quintillion molecules per cc, 25 quintillion. That's 25 quintillion, that's quintillions with a Q. Interstellar space is roughly 25 quintillion times emptier than the air around you. It's emptier than any vacuum chamber ever constructed on Earth. It's not just empty, it's empty at a level that's almost incomprehensible. And in this near-perfect vacuum, there are no landmarks, no gravitational harbors, no resources to harvest, no places to stop, no way stations, no convenient gas stations where you can refuel. Nothing between Earth and Proxima Centauri except cold, radiation, darkness, and distance. Section 5A, the navigation problem. This emptiness creates a navigational reality that has no parallel in spaceflight history. Every mission humanity has ever flown, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, every single one has used the gravitational fields of planets, moons, and the sun as tools. Gravity assists are a technique where a spacecraft passes near a celestial body and uses its gravitational field to redirect and accelerate the spacecraft. The Voyager probes used Jupiter, Saturn, Uranus, and Neptune to build speed across the outer solar system without burning additional fuel. Cassini looped past Venus and Earth before reaching Saturn. These maneuvers work because the solar system is full of gravitational infrastructure, massive bodies whose gravitational fields can be borrowed and exploited by a passing spacecraft. But interstellar space has no such infrastructure. Between the outer edge of our solar system and the outer edge of the Alpha Centauri system, a journey lasting decades or centuries, there are no planets, there are no moons, there are no stars, there are no significant gravitational fields of any kind. The ship cannot perform gravity assists. It cannot slingshot around a convenient gas giant to correct a navigation error or boost its speed. It cannot borrow gravitational energy from anything because there's nothing there. Every change of velocity, every course correction, every adjustment to the flight path must be accomplished by burning fuel that the ship carried from Earth. Fuel that is finite. Fuel that is irreplaceable. Fuel that is already allocated for the critical deceleration phase at the destination. This creates a terrifying scenario. Imagine the spacecraft is 100 years into its 400-year journey when the navigation system detects a small error. The ship is slightly off course, not drastically, just 1/10,000th of a degree off, tiny error. But over a journey lasting centuries, tiny errors compound into enormous deviations. That 1/10,000th degree error translates into a missed distance of billions of miles by the time the ship reaches Proxima Centauri. The navigation system tells the crew they need to correct their course. So the crew burns fuel to correct the trajectory. They burn fuel that was allocated for decelerating at the destination. They have to make a choice, correct the navigation error now, or arrive at the destination traveling at a fraction of light speed. unable to stop, unable to enter orbit, unable to do anything except flash through the star system and continue into the void on the other side. This is the navigation trap. The ship must navigate with extraordinary precision across distances, where even tiny angular errors compound into enormous positional deviations. The navigation system must function continuously and accurately for the entire transit, decades, centuries, whatever the journey requires. It must correct for the gravitational influence of passing stars, the drift of the destination star through the galaxy, and the spacecraft's own structural flexing, thermal deformation, and thrust asymmetries. Any period of navigational blindness, caused by sensor failure, computer malfunction, or crew inability to operate the guidance systems, could leave the ship drifting off course with no way to recover, except by burning fuel it can't afford to spend. And the ship can't stop, it can't pull over to the side of the road. If a critical system fails and requires months or years of repair, the ship continues hurtling through the void at whatever velocity it has achieved, covering millions of miles while the crew scrambles to fix what's broken. There's no safe harbor, there's nowhere to park, there's no emergency lane. A ship crossing this void would be in perpetual motion, unable to stop, unable to rest, unable to take a break from the journey that is consuming its fuel, degrading its systems, and slowly killing everyone aboard. Section 5B, the closed loop problem. The next problem is almost worse. A ship crossing interstellar space would be the most isolated object in human history. Not isolated like a submarine beneath Arctic ice, which can surface and radio for help. Not isolated like a research station in Antarctica, which receives supply flights and sits on a planet teeming with life. Not isolated like the International Space Station, which can resupply every few weeks and perform evacuations within hours. Isolated in an absolute sense that has no precedent in human experience. The ship would carry every molecule of air its passengers will ever breathe, every drop of water they will ever drink, every calorie of food they will ever consume, every spare part they will ever need, every tool required to manufacture anything that breaks. Nothing comes in from outside. Nothing arrives to replenish what is lost. The ship is the entire world. And if the ship fails in any way, if any critical system breaks down irreparably, there's no rescue, there's no hope. Imagine a scenario. 150 years into the journey, the primary water recycler fails. This is the system that takes human waste, urine, sweat, tears, all the water that passes through the human body, and recycles it back into drinking water. It's an incredibly complex system with thousands of parts and trillions of chemical reactions per second. The backup system kicks in, but backup systems are redundant for emergencies only. They're not designed to run indefinitely. If the primary system can't be repaired, the crew has to maintain life support on a backup system that was never meant for long-term operation. They try to fix the primary system, they spend months, maybe years, trying to repair it, but they don't have a replacement part because spare parts are limited. They can't manufacture the part because it requires materials they don't have. The backup system is slowly degrading. Water supplies are being consumed without replacement. The crew is rationing water, but rationing only slows the inevitable. Eventually, the water runs out. And there's no help coming. There's no rescue mission. No supply ship. No emergency water being sent from Earth. Just the slow realization that the spacecraft's life support is failing, and there's nothing anyone can do to stop it. This is the closed-loop problem. Every system must function perfectly for the entire duration of the mission. Redundancy helps, but redundancy eventually fails too. All machines break. All systems degrade. And in interstellar space, there's no outside help. There's no reset button. There's just the slow accumulation of system failures until something catastrophic happens. Section 5C, the radiation problem. But the most devastating problem might be the radiation. The void of interstellar space is saturated with something called galactic cosmic radiation, a relentless bombardment of high-energy particles that originates from supernova explosions and other violent events scattered throughout the galaxy. These particles, mostly protons, helium nuclei, and heavier ions of elements like iron and carbon, travel at nearly the speed of light and carry enormous energy. and they will slam into the ship and everything inside it, every single second of every single day, for the entire duration of the mission. Inside the solar system, the heliosphere provides partial shielding against these particles. The heliosphere is like an umbrella made of solar wind that slightly deflects cosmic radiation. It's not perfect protection, but it reduces the dose. Outside the heliosphere, that protection vanishes. The full, unfiltered intensity of galactic cosmic radiation becomes the crew's permanent environment. Conventional spacecraft shielding offers limited protection against these particles. Unlike solar particle events, which consist primarily of lower energy protons that can be blocked by a few centimeters of material, galactic cosmic ray nuclei carry so much energy that they penetrate deeply through metal, through water, through polyethylene, through every practical shielding material. Worse, and this is the really bad part, when heavy cosmic ray particles strike shielding material, they don't just stop. They produce showers of secondary particles that can be even more biologically damaging than the original particle. Adding more shielding doesn't necessarily reduce the dose. In some configurations, it increases it. The shield becomes a source of additional radiation. NASA considers space radiation the #1 health risk for deep space exploration. Number 1. More dangerous than decompression. More dangerous than micrometeorite impacts. More dangerous than any other hazard space poses. And no current shielding concept has been shown to reduce space radiation to acceptable levels. What does this radiation actually do to living tissue? It shreds DNA. The cosmic ray particles slam through your cells at nearly light speed, and as they pass through, they tear apart the genetic material that makes you who you are. Your body has repair mechanisms. DNA damage happens to everyone. We're exposed to background radiation constantly. Your cells have enzymes that can repair some of this damage. But when the radiation dose is continuous and intense, the repair mechanisms become overwhelmed. The damage accumulates. Over months or years of exposure, accumulated radiation damage leads to several catastrophic health outcomes. Cancer is the obvious one. Higher radiation exposure dramatically increases cancer risk, but it doesn't stop there. Radiation damages the nervous system. Neurons are sensitive to radiation, and cumulative damage can lead to cognitive decline, to reduced processing speed, to difficulty concentrating. An astronaut could arrive at their destination after centuries of travel. Radiation sickness, cancer, cognitive decline, organ damage, all from decades of exposure to galactic cosmic rays. There's no medical treatment that can reverse this damage because the damage is at the cellular level, in the very structure of their DNA. The crew isn't just fighting the void, the isolation, the closed-loop systems, and the navigation problems. They're fighting radiation that's slowly destroying them from the inside out, day after day, for the entire duration of the mission. Part 6. Potential Solutions and Their Failures. By now, you're probably thinking, well, there must be some solution to these problems, right? Humanity is incredibly creative. We must have some way to solve the radiation problem, the psychological problem, the maintenance problem. And the answer is, not really. We have some ideas, but none of them actually work. Let's talk about some of the proposed solutions and why they fail. Section 6A, Cryogenic Sleep. One popular science fiction concept is cryogenic sleep. You put the crew in suspended animation. They sleep for the entire 200-year journey. Their metabolism shut down. They don't age, they don't consume resources. They just sleep, and then they wake up when they arrive at the destination. This idea has profound appeal. It makes the problem seem solvable. If the crew doesn't need to be awake, if they don't need to eat or breathe or think or feel, then the interstellar problem becomes much smaller. Except it doesn't work. First, cryogenic sleep has never been successfully demonstrated in humans. We have no idea if the human body can be frozen and revived without catastrophic damage to the brain and organs. We have no technology for this. It remains pure science fiction. Second, even if cryogenic sleep were possible, the spacecraft still needs to be maintained. Systems still need to be monitored. The spacecraft still needs to navigate. Someone has to stay awake. And if someone has to stay awake, they face all the problems we've already discussed: isolation, radiation exposure, psychological strain, and the maintenance problem. Third, the water recycler still breaks. The radiation shielding still degrades. The navigation system still needs corrections. And the skeleton crew of awake astronauts, managing systems for decades, will themselves experience radiation damage, cognitive decline, and psychological deterioration. Cryogenic sleep doesn't solve the interstellar problem, it just pushes the problem onto the smaller crew that has to stay awake. And that's an even worse outcome, because that crew bears all the radiation dose, all the isolation, all the psychological strain, while the rest of the crew sleep safely. Section 6b. Time dilation. Another proposed solution is time dilation. According to Einstein's theory of special relativity, time passes more slowly for objects moving at high velocities. If a spacecraft could travel at, say, 99.99% the speed of light, time would pass much more slowly aboard the spacecraft than on Earth. So from the crew's perspective, a 400-year journey might feel like only 40 years of subjective time, or 4 years, or even less. The crew ages much more slowly than people on Earth. They experience less radiation damage because less time has passed for them. The psychological burden is reduced because it doesn't feel like 400 years. It sounds perfect, but it comes with a devastating cost. The crew becomes temporal exiles. When they arrive at Proxima Centauri after what felt like 40 years of travel, 400 years have passed on Earth. Their families are long dead. Their civilization might have changed beyond recognition. The technology they left Earth with is ancient by the time they arrive. Worse, they arrive to find that Earth's civilization might have already surpassed them. If humanity on Earth continues advancing technologically, the interstellar travelers might arrive at their destination only to discover that robotic probes or other spacecraft sent from Earth millennia later have already explored the star system. They might arrive to find that humans, descendants of their great-great-great-grandchildren, have already established colonies using technology far more advanced than the ship they're flying. Time dilation turns interstellar travel into a one-way ticket to temporal exile. You leave Earth, you feel like decades have passed, and you arrive to find that centuries have passed, and your entire civilization has moved on without you. The sacrifice becomes even more profound than a traditional long-term mission. And practically speaking, time dilation requires the spacecraft to travel at velocities that our propulsion systems might never be able to achieve. All of our optimistic propulsion concepts max out at 5 to 10% of light speed. Time dilation significant enough to be meaningful requires speeds in the 90% plus range. We're not there yet, and we might never get there. Section 6c. Artificial intelligence. The final proposed solution is to replace the human crew with artificial intelligence. Send robots instead of people. Send AI systems capable of learning, adapting, and solving problems. Let the robots make the journey, and we avoid all the human problems. Radiation damage, psychological strain, maintenance problems, knowledge degradation. Robots don't get depressed. They don't lose motivation. They don't need psychological support. It's technically plausible. I could potentially solve the interstellar problem much more effectively than humans could. But it comes with a fundamental problem. If we send robots to another star instead of humans, we've abandoned the goal of human space exploration. We've abandoned the dream of humanity spreading across the stars. The entire impetus for interstellar travel is the question: can human beings survive beyond Earth? Can we build a new world on another planet? Can we achieve the age-old dream of visiting the stars? If we send robots, those questions remain unanswered. The robots might build a civilization on another planet, but it's a civilization of machines, not humans. There is a profound difference between AI robots reached Proxima Centauri and humans reached Proxima Centauri. One is a technological achievement. The other is a statement about humanity's future. The latter is the dream that drives the entire concept. And practically, AI has its own problems. AI systems require power to run. They require maintenance. They can malfunction. They can corrupt. A spacecraft of autonomous robots still faces the closed-loop problem, the navigation problem, the radiation shielding problem. All the physical problems remain, just with different operators. So the proposed solutions don't work. Cryogenic sleep is speculative and doesn't solve the maintenance problem. Time dilation turns the crew into temporal exiles and requires technology we might never develop. AI abandons the entire premise of human space exploration. Which brings us to the core question: can humans actually survive an interstellar mission? Part 7. The final answer. The answer, I think, is uncertain, and that uncertainty might be worse than a definitive no. The physical problems are solvable, at least theoretically. We could build better radiation shielding. We could develop better life support systems. We could improve spacecraft construction. We could solve the technological problems if we had infinite time and infinite resources. But the human problems are not solvable. We can't solve radiation damage to the human brain because it's happening at the cellular level. We can't prevent psychological degradation from decades of isolation because it's rooted in fundamental aspects of human psychology. We can't guarantee that knowledge will transfer across dozens of generations because knowledge loss is a natural human phenomenon. An interstellar spacecraft would be the most difficult human endeavor ever attempted. It would be harder than colonizing Antarctica. It would be harder than surviving in a submarine under ice. It would be harder than any expedition in human history because there's no possibility of rescue, no possibility of going home, no safety net at all. Could humans survive it? Maybe, if we selected the right crew, if we had perfect leadership across multiple generations. If every system performed flawlessly for centuries, if the crew somehow managed to preserve knowledge and motivation despite the profound isolation. Maybe. But more realistically, an interstellar mission would be a journey toward human transcendence or extinction, with very little middle ground. The crew would either adapt to the conditions through some biological or cultural change we can't predict, or they would slowly degrade and fail. The void of interstellar space doesn't just kill bodies. It strips away all the things that make us human, our connections to place, our connection to a broader civilization, our sense of safety, our psychological stability. It's a filter that only the most resilient, most adapted humans could pass through. And that's the real horror of interstellar travel. It doesn't just test engineering. It tests whether human beings can remain human across a void that erases every safety net our species has ever known. Closing sequence, 58005900. So could humans actually survive a real interstellar mission? The answer is, we don't know. But we're beginning to understand why it might be impossible. And that understanding, that confrontation with the limits of human capability, might be the most important thing we learn from this exercise. We are creatures of Earth. We evolved under gravity. We evolved with the sun overhead. We evolved to live in communities with thousands of other humans. We evolved to see horizons and taste fresh water and feel wind on our faces. We evolved for connection, for belonging, for home. Interstellar travel would strip all of that away. It would put us in a vacuum without any of the things that make us feel human. And it's an open question, a genuinely uncertain question, whether we could survive that psychologically and physiologically. But you know what? The fact that we're asking the question, the fact that we're thinking about it, the fact that we're willing to contemplate the possibility of sending our descendants into the void to touch another star, that itself is extraordinary. That itself is beautiful. Because it means that even in the face of impossible odds, even confronted with the prospect of centuries of suffering and uncertainty, humanity still dreams of the stars. We still reach. We still hope. And maybe, just maybe, that hope is enough to sustain us through a void that seems designed to crush it. Thank you for watching. If you enjoyed this journey through the cosmos and the limits of human endurance, please hit that like button and subscribe for more explorations of how science reshapes our understanding of the universe and ourselves.